Okay, so there you go. There he is. There's a scheme that works. And you even have a way to do this thing. Now, let's do one more, leapfrog. I want to show you that one's, because I still don't feel quite the love yet for von Neumann that he deserves. I don't sense it at all, actually. So we're going to keep going at this. And call me crazy if you wish, but I think, you just keep working these things and eventually you find love. They say love is a commitment. I'm showing you what that means right now. Okay? So let's come back over to here and let's talk about what it meant to do leapfrog. So leapfrog was basically, again, same scheme. Let's go back to here. Let's put the M's. And now, that's it. Remember, leapfrog said, what I'm going to do is, it's not just about what my current time is, it's about one time back as well. So my point in the future is what it was one time ago plus the derivative at the current time. Okay? That was the basic scheme for that. And now you see lambda here. And part of the reason to show you this again is just to see, how does this all work out? We presented 5 or 6 different techniques for solving this equation. And it's, like I said, it is so important for you to figure out before you start plowing ahead that there is this idea of CFL, that this lambda is the most important thing you're going to control in your problem. Okay? And that's, hopefully this is the thing that that's supposed to be the take-home message. All right. I'm sure that's what you're going to take home. All right. So leapfrog. Same thing, right? You get this, in fact, ready? I feel a G of M everywhere. Does everybody feel that? Can you feel it in your gut? I feel it right here. Right here. I'm pinning this right just a little to the right. Okay? It's not even a... So I'm going to get it. If I divide by G of M, I'm going to get left over with a G. And I feel I need to multiply by e to the minus I C of N H. Do you feel that? Do you feel it right here? Right here? No? Okay, so this is why we do this, because you start getting in. This is what's called intuition. Or laziness, whatever. Look at that, a G. A 1 over G. Why do I get 1 over G? Because that was evaluated one time ago at G of M minus 1. And I just divided by G of M, so I get that. See, it changes the structure right away of how G is going to behave in the system. And plus lambda. And since I already divided by G of M, the only thing I got left over in here are things like e to the I zeta h minus e to the minus I zeta h. That's after we do some algebra. That's what you're going to get, just using the same steps as before. Okay? So, this is going to then be G is equal to 1 over G plus 2I lambda sine theta h. And if I wanted to, I can multiply everything by G. And so I'm going to get G squared minus 2I lambda sine theta h minus 1 equals to 0. That's what I get. So I get an equation for G, right? Quadratic equation for G. And what you try to find from this quadratic equation for G is, where does this happen? It turns out it happens when, and I'm not going to go through it, when lambda is equal to less than 1. Okay? All right, so these are the techniques. This is how you start evaluating schemes. Should I do it or not? Now, we made all this fuss about this. Now, let's get real. Yeah? Mm-hmm.
These all depend on these concepts such as G to the M times the Fourier mode. Is that a legitimate? That's a Fourier coefficient, right?
Yes. So we're going to talk about, is this legit?
Okay.
Right now. Because in some sense, we're saying, hey, look at that, no. It gives us one measure. So here's the reality of what you're dealing with. Make little bullet points. Just because you did it doesn't mean that actually it means it's stable provided your solution actually sort of can be written in these forms. Okay? So it doesn't guarantee you stability. What it can tell you, what you're looking for this is a test of instability, not stability. This only tells you, oh, you know, it's not obvious it's going to blow up on you. That's all it tells you, really. It doesn't guarantee it's going to work. You come up with a scheme, hey, the von Neumann says it's not going to blow up. That doesn't mean it's not going to. This means it's not going to blow up that way. Okay? So it's necessary but not sufficient. Don't you love that terminology? That's a great math term. Just like the Taylor series or the Newton method, no, it always works provided you're sufficiently close. Okay? So it is necessary that you have this, but not sufficient. Okay, that's fact one for you. There are other instability mechanisms. That are not captured by the von Neumann analysis. Again, the von Neumann's captured one type of instability. That's it. So it kind of relates back to one. So you're not going to capture all the instability mechanisms with this. You put a little nonlinearity in there, kills it off. You can't, von Neumann's dead, right? You have an equation with a little bit of nonlinearity. It'll kill off your von Neumann analysis. Why is that? Notice what we did. What we did is we came over here, and the reason it kind of worked is because this was linear. We could divide out g of m's. We could multiply by e to the negative i's, and everything just dropped out. And the only reason it dropped out is because it was linear. You put a little nonlinearity in there, and now, for instance, if you had a term like a u squared, instead of having e to the I c of h's, now this is going to produce e to the I 2I sigma. It's going to create harmonics, which just sit around and live, and you can't kill them. You're dead. Von Neumann does not work for nonlinearity. Now, of all these, I think that's the most important one. Also, non-constant coefficient doesn't work either, right? Nonlinearity or non-constant coefficient. Now, let me make an observation, perhaps. If you're trying to really work hard at solving a linear constant coefficient PDE, you come see me. I'll write down the solution for you. I can write down the solution to any linear constant coefficient PDE. Here it is. You are not in a position that you need to be doing all this simulation. Okay? Yet, this von Neumann analysis only works right there, where I can already solve the problem. So you see how limited vanillity is? I didn't even say it. Limited vanillity. That means you ran out of vanilla. Okay? Look it up in the dictionary. But it's fine. I mean, so if you take a numerical analysis course, so this is not a numerical analysis course. This is about scientific computing, which is a little different. People spend a lot of time doing this kind of stuff, showing this really works. We can nail it down. We can prove it's going to do all this stuff. And you're like, yeah, for a problem I could solve ahead of time. I'll give you a problem that I can't solve. That's why I need the computer. And they say, oh, I can't do anything with it. Okay? So there's a problem. There's a disconnect. And finally, here's my rule of thumb. Rule of thumb, okay, is worry about the accuracy. It's a little bit like when my daughters fight, and they worry about, oh, that wasn't fair because you didn't. And it's like, listen, just worry about yourself. It's the same concept here. Don't worry as much about the stability. And here's why. Because you know what? If you have an equation that's worth putting on the computer and you're going to go solve this thing up, you're not going to get this von Neumann analysis telling you anything. You concentrate on the accuracy. What kind of accuracy do I want? What kind of schemes do I want to step forward with? Hey, you know what? I like OD45. Why? Because it's fourth order accurate. And you know what? I want to take spatial derivatives. Tell you what, I'll do fourth order accurate derivatives because that's the kind of accuracy I want. Focus on that. Most of the time, what happens is, if you have an unstable scheme, you start running it, and it just announces itself to you. We're going to see this in class. If it's unstable, stuff blows up. And you go, oh, my scheme must be unstable. It's not that hard to do deductive reasoning. It's faster to do this than trying to think about how would I cook up some kind of von Neumann analysis for a nonlinear problem. Okay? So this is good. I want you to have this concept in your head so at least you sound well educated, like, you know, because you like go to a learned party. Hey, how you doing? How's that beer? Good. Hey, how's that von Neumann analysis? And then you know what they're talking about because that's what they always say when they're tapping that keg. Okay? So I want you to not go like, what's he talking about? And you go, oh, you're educated. Oh, you're keeping it before that CFL number in check? I'll get them. Okay? So you should know about it. You should have proper education. On the other hand, you should also know that it's limited. What it's going to be able to tell you about your problem is very limited when you're not solving something trivial. Okay? That's about all I have to say about that. So, questions on that today? Everybody good? Everybody's good. And how's homework going? Everybody's good? Calculating some derivative matrices. These are going to be your weapons, by the way. I'm just telling you, you got 3 forearms on that one. A, B, C. When you create these, you should just start. You're going to start. Yeah, I know. You can feel it, don't you? Do you feel it? Do you feel the love for it? Forearm shivering on the next homework. Okay.